All right, let's dive right into this explainer. If you've ever geeked out over what's actually happening inside an EV battery pack to keep it running smoothly and safely, you are absolutely in the right place. Today, we're unpacking the incredibly intense engineering specifications behind EV battery protection. We're going to take you on a journey from catastrophic physical threats all the way down to the ironclad engineering shields designed to literally stop them in their tracks. We are getting deep in the actual technical specs that engineers use to govern battery health. Here's our roadmap for today. 1. Root causes of battery imbalance. 2. Diagnostic architecture and fail-safes. 3. DFMEA key design prevention. 4. PFMEA manufacturing process control. And 5. DVP and R mass verification. Starting with Section 1. Root causes of battery imbalance, or what we're calling the catastrophic threats. Now, these root causes represent a severity 7 risk to the entire system. There is this terrifying moment recognized in the engineering specs as consistency divergence, specifically tagged as BMS W015. This is the exact second a battery's internal imbalance literally outpaces the system's natural healing ability. You see, standard passive balancing circuits can usually only bleed off less than 100 milliamps of excess current. When the differences between individual cells get too large, that tiny 100 milliamp fix just doesn't cut it anymore, and the battery pack essentially begins to drift apart. It's a cascading failure, reacting like a ticking clock. It usually kicks off with a physical roadblock, like a patch of uneven cooling paste that creates a thermal dead zone. Because of joule heating, the heat gets trapped there. And if the temperature difference between cells exceeds just 3 degrees Celsius, well, the laws of chemistry take over. According to the Arrhenius equation, all that excess heat causes the cell's internal SEI film to rapidly thicken. So you lose active materials, the capacity drops, and boom, you get severe voltage divergence between that hot cell and its cooler neighbors. But beyond just trapped heat, we also have to worry about internal electrical threats. Think of them as invisible leaks. For example, metallic impurities or tiny microscopic burrs left over from manufacturing can actually pierce the internal separators, and that causes micro short circuits. These shorts create this extreme self-discharge rate that just constantly drains the cell. On top of that, the very MOSFET chips on the circuit board that are supposed to balance the battery can suffer thermal breakdown from the constant high-temperature stress, completely knocking out their ability to fix the imbalance. Moving on to Section 2. Diagnostic architecture and fail-safes, the ironclad immune system. To catch these catastrophic threats before they blow up, the battery management system runs 2 diagnostic models at the exact same time. It uses an extended Kalman filter to dynamically track the battery's state and pairs that with an open circuit voltage model that relies on static correlations. But here is the genius part. Temperature gradients can easily cause false impedance readings. So if the system detects a temperature delta of more than 3 degrees, the algorithm dynamically switches over to specific high-temperature lookup tables. This thermal coupling completely prevents the system from triggering annoying false diagnostic alarms. The really crucial piece of the puzzle here is the derating map, known in the specs as BMS A005. If the cells get dangerously out of whack during a fast charge, the strong cells could overcharge and cause lithium plating, and that is a super fast track to thermal runaway. To stop this, the safety layer aggressively steps in. It rigidly hard limits the maximum state of charge to between 80 and 90%, and it slashes the charging current down to 5 amps or even 0. It literally physically blocks the energy from pushing the system over the edge. All right, Section 3, DFMEA Key Design Prevention, the genetics of safety. To handle these massive energy mismatches without literally melting the circuit board, standard 100 milliamp passive balancing sometimes just isn't enough for high-end systems. Engineers actually have to design active balancing architectures capable of transferring more than 1 full amp of power. To pull this off, they use worst-case circuit analysis to perfectly size the resistors and heat dissipation profiles, making absolutely sure the PCB won't carbonize under the stress of moving all that energy around. And this brings us to the key-off strategy. You probably think your EV is totally off when you park it, right? Well, the BMS definitely isn't. The system uses background micropower algorithms to silently wake up the BMS while your car is sleeping. By utilizing those long hours sitting in the driveway, it meticulously repairs those microimbalances, essentially giving high self-discharge cells the extra bump of charge they need before you even start your morning commute. Section 4. PFMEA Manufacturing Process Control, Building the Perfect Shield. We all know manufacturing variation is public enemy number one. So to combat it, factories use rigorous 100% dual CCD and 3D automated optical inspection. They are visually monitoring every single millimeter of the thermal cooling glue to check for tiny bubbles or voids, making sure those fatal thermal roadblocks never form in the first place. On top of that, they use a centralized MES database to track the exact assembly pressure applied to every single module, ensuring the physical compression doesn't slowly crush the battery materials over time. The sheer rigor here is just wild. Before they even think about assembling the pack, every single cell is forced through a mandatory 14-day high-temperature aging test. This is purely to track the cell's voltage drop over a 2-week period. By mathematically calculating the self-discharge rate, or the K value, they can flawlessly weed out any cells hiding microscopic short circuits before they ever make it into a consumer's vehicle. Finally, Section 5, DVP and R mass verification, the ultimate stress test. First up, they test the absolute thermal limits of the balancing circuits. The system is shoved into an environmental chamber set to a blistering 85 degrees Celsius, with all balancing channels pushed to 100% capacity for 24 continuous hours. It is brutal. After this test, the circuit boards cannot show a single sign of carbonization, melting, or solder fatigue, and the resistor values aren't allowed to drift by more than 1%. Next, we have the thermal response test. Engineers will actually sabotage a battery pack by intentionally removing 30% of the cooling paste to create a hotspot. If local temperatures spike and the difference between cells exceeds 3 degrees, the software is given a mere 10 seconds of debounce time to recognize the fault. Within those 10 seconds, it has to blast the cooling pumps and fans to 100% capacity to pull that heat out. Then comes the fast charging test. While plugged into a simulated high-power charger, engineers inject a severe 350 millivolt artificial deviation right into the system. The BMS has exactly 500 milliseconds to slam on the brakes. In just half a second, it has to trigger the alarm, communicate with the charging station via the CAN bus, and strictly cut the charging current down to safe limits, entirely preventing an overvoltage explosion. And lastly, they verify the sleep mode. While it's silently waking up to balance the cells when parked, the system's static dark current draw from the low voltage network must remain strictly below 50 milliamps. This guarantees that while the high-voltage battery is doing its self-healing routine, it doesn't accidentally drain your 12-volt auxiliary battery and leave you stranded on a Monday morning. So, as we wrap up this explainer, we can clearly see how this massive engineering iceberg creates an invisible ironclad shield around the battery. It's a truly brilliant orchestration of chemistry, software, and mechanical design all working in perfect unison. It really leaves you wondering about the sheer scale of the engineering beneath the surface, doesn't it? Then next time you see an EV silently gliding down the street, ask yourself, how many micro decisions is that vehicle making every single millisecond just to protect its passengers and its power source? The depth of these specifications proves that the true innovation isn't just in the battery's power, but in its protection. Thanks so much for joining me on this explainer, and keep questioning what's under the hood.